Chapter 2 Aerodynamics Introduction This chapter focuses on the aerodynamic fundamentals unique to weight shift control (WSC) operations. The portions of the Pilot's Handbook of Aeronautical Knowledge, faa-h-8083-5, on principles of ight and aerodynamics apply to WSC and are a prerequisite to reading this chapter. Aerodynamic Terms Airfoil is the term used for a surface on an aircraft that produces lift, typically the wing itself. Although many different airfoil designs exist, all airfoils produce lift in a similar manner. Camber refers to the curvature of a wing. When looking at a cross-section, a wing possesses upper camber on its top surface and lower camber on its bottom surface. WSC airfoils can be single surface, with one piece of fabric for most of the airfoil, for slower wings. Faster airfoils have two surfaces and are called double surface wings, which are more like an airplane wing. Figure 2.1. This double surface allows the wing structure to be enclosed inside the wing, similar to an airplane wing, reducing drag and allowing for faster speeds for the same thrust. The leading edge is the forward edge of the airfoil, and the rear edge of the airfoil is called the trailing edge. The chord line is an imaginary straight line drawn from the leading edge to the trailing edge. The WSC airfoil typically uses a different camber with the airfoil high point farther forward than the airplane airfoil, creating a more stable airfoil. Figure 2.2. The WSC wing is a unique design of airfoils that differ throughout the wingspan. Looking at a top view of the wing, in the center is the wing root and on each end is the wingtip. Wing chord is any section of the wing parallel to the wing root. Figures 2.3 and 2.4, the wingtip chord is the chord where the trailing edge is furthest to the rear of the wing. This can be inboard of the tip, as shown, and can vary depending on the specific wing design. The nose angle is the angle made by the leading edges, typically ranging from 120 degrees to 130 degrees. Sweep is the angle measured between the quarter chord line of 25% chords, and a line perpendicular to the root chord. Figure 2.3. Looking at the rear view of the wing, anhedral is the angle the wings make angling down and dihedral is the angle the wings make angling up. Figure 2.5. Dihedral is the positive angle formed between the lateral axis of an airplane and a line which passes through the center of the wing. Anhedral is the similar negative angle. Wings with sweep have an effective dihedral characteristic that counteracts the physical anhedral to develop the required roll stability for the particular make/model design objective. This is explained in the Pilot's Handbook of Aeronautical Knowledge in much greater detail for further reference. Unlike airplanes which typically have significant dihedral as viewed from the front or back for roll stability, WSC wings typically have a slight amount of anhedral as shown in Figure 2.5 and effective dihedral, which is a characteristic of the swept wing design. Wing twist is the decrease in chord angle from the root to the tip chord, common to all WSC wings and ranging from 5 degrees to 15 degrees. This wing twist is also called washout as the wing decreases its angle of attack from root to tip. The term billow was originally used for the early Rogallo wings as the additional material in degrees that was added to the airframe to create the airfoil. It is still used today to define the amount of twist or washout in the wing. The WSC may not have twist/washout when sitting on the ground, and must be FL-ying and developing lift to display the proper aerodynamic twist characteristic of WSC wings. Figure 2.6. The longitudinal axis is an imaginary line about which the aircraft rolls around its center of gravity, c.g. it is also called the roll axis. The longitudinal axis is not necessarily a phi cross line through the carriage because the roll axis changes for different FL-ight configurations, but can be approximated by the middle of the propeller shaft for a properly designed WSC aircraft and is typically parallel with the FL-ight path of the aircraft as shown in Figure 2.7. Angle of incidence is the angle formed by the root chord line of the wing and the longitudinal axis of the WSC aircraft. Unlike that of an airplane, the WSC angle of incidence has a significant change in FL-ight because the carriage is attached to the wing, which allows the wing to rotate around the carriage hang point on the wing and is controlled by the pilot as shown in Figure 2.7. Pitch angle is the angle the WSC wing root chord, center of wing, makes with the Earth's horizontal plane. Many pilots confuse the pitch angle, which is easily seen and felt, with the angle of attack, AOA, which is not as perceptible. For example, if FL-ying in a glide with the engine idle and the nose lowered, the pitch angle can be below the horizon. Another example would be FL-ying at full power climb with the nose raised, resulting in the pitch angle being well above the horizon. Figure 2.8, pitch angles are covered in greater detail in Chapter 6. Deck angle is the angle of the cart's wheel axles to the landing surfaces, as in the powered parachute, PPC deck angle. Relative wind is the direction of the airflow with respect to the wing. It is parallel to and opposite the WSC ight path. Relative wind may be affected by movement of the WSC through the air, as well as by all forms of unstable, disturbed air such as wind shear, thermals, and turbulence. When a WSC is FL ying through undisturbed air, the relative wind is parallel to and opposite the ight path. Figure 2.7, OA is the angle between the relative wind and the wing chord line. Because of the wing twist, the OA is greatest at the wing root and decreases along the wingspan to the tips. This is an important concept covered in the stability section of this chapter. For changing speeds during gliding, level FLight, and climbs, OA is the primary control for speed changes. Lower angles of attack produce higher speeds, and higher angles of attack result in slower speeds. The pilot changes the OA by moving the control bar forward for high angles of attack and slow speeds as shown in Figure 2.7, top, for high angle of incidence and Figure 2.8, top, for high pitch angle. Low angles of attack for fast speeds are shown in Figure 2.7, bottom, for low angle of incidence and Figure 2.8, bottom, for low pitch angle. Most of the time, the pilot is FL ying at the cruise OA, which is the trim position of the control bar, and the pilot is neither pushing out nor pulling in on the control bar. This trim position is the OA and speed the aircraft FLIES if the pilot is FL ying straight and releases the control bar in calm air. Figure 2.9, middle, planform is the shape or form of a wing as viewed from above. The WSC wing comes in a number of planforms ranging from the larger and slower wings to the smaller and faster wings. Aspect ratio is the wingspan divided by the average chord line. A WSC aircraft with a common 200 square foot training wing, about a 35-foot wingspan, and with a typical mean chord line of 7 feet, would have an average aspect ratio of 5. This relatively low aspect ratio is less efficient at producing lift. A higher performance wing with 140 square feet, a 35-foot wingspan, and an average 5-foot average chord would have an aspect ratio of 7. The WSC wing is similar to airplane wings in that the aspect ratio differs with the specific design. Mission for the aircraft. For the same wing area and similar design, the lower aspect ratio wings produce less lift and more drag, higher aspect ratio wings produce more lift, less drag, and may require more pilot effort to FLY, depending on the design. Figure 2.10, wing loading is a term associated with total weight being carried by the wing in relation to the size of the wing. It is the amount of load each square foot of the wing must support. Wing loading is found by dividing the total weight of the aircraft, in pounds, by the total area of the wing, in square feet. For example, the wing loading would be 5.0 pounds per square foot when 1,000 pounds total weight for a 2-seat WSC aircraft with 2 people is supported by a 200 square foot wing. If FL ying the same wing with 1 person and a lighter total weight of 500 pounds, the wing loading would be 2.5 pounds per square foot. In the small, high-performance wing of 140 square feet loaded at 1,000 pounds, wing loading would be 7.1 pounds per square foot. Gliding FLight is FL ying in a descent with the engine at idle or shut off. For example, use a glide ratio of 5, which is 5 feet traveled horizontally for every foot descended vertically. Glide ratios vary significantly between models. WSC wing flexibility. The WSC wing retains its rigid airfoil shape due to rigid preformed ribs called battens, which are inserted from the root to the tip along the span of the wing, similar to ribs for an airplane wing, and a piece of foam or mylar running along the top side of the leading edge to the high point, which maintains its front part of the airfoil shape in between the battens. Figure 2.11, some WSC double-surface wing designs use a rib similar to a PPC wing that attaches to the lower surface and the upper surface to maintain the wing camber in addition to the battens. Even though the airfoil sections are rigid, the WSC aircraft is called a FLX wing for 2 reasons. First, it is designed so the outboard leading edges FLX up and back when loaded. The FLXing of the outboard section of the wing also allows load relief because the tips increase twist and decrease OA. The greater the weight, the greater the FLX and wing twist. This FLXing allows the WSC aircraft to automatically reduce loads in unstable air, providing a smoother ride than a rigid wing. Since the wing FLXs and reduces the load for a given angle of attack at the root chord, WSC aircraft cannot obtain loads as high as those obtained by a rigid wing. This FLXing of the outboard leading edges also assists in initiating a turn. Second, the wing is designed to FLX as it changes twist from side to side for turning, historically known as wing warping. WSC wing warping is similar to what the Wright brothers did on their early aircraft, but they did it with wires warping the wing. The WSC aircraft uses no wires and warps the wing by shifting the weight, which is covered in Chapter 3, Components and Systems. This flexibility is designed into the wing primarily for turning the aircraft without any movable control surfaces like the ailerons and rudder on an airplane. Forces in flight. The four forces that affect WSCFLite are thrust, drag, lift, and weight. Figure 212, in level, steady WSCFLite, 1. The sum of all upward forces equals the sum of all downward forces. 2. The sum of all forward forces equals the sum of all backward forces. 3. The sum of all moments equals 0. Note that the lift and weight forces are much greater than the thrust and drag forces. A typical example for many WSC aircraft is that the lift/weight forces are 5a times the thrust/drag forces. Thrust, the forward force produced by a powerplant/propeller as it forces a mass of air to the rear, usually acts parallel to the longitudinal axis, relative wind, and flight path. Drag, the aerodynamic force acting on the wing and carriage in the same plane and in the same direction as the relative wind. Lift, the aerodynamic force caused by air flowing over the wing that is perpendicular to the relative wind. Weight, the force of gravity acting upon a body straight down and perpendicular to the earth. During level flight, these forces are all horizontal and vertical. During descents or climbing, these forces must be broken down into components for analysis. Dynamic pressure Q, both lift and drag are a direct result of the dynamic pressure of the air. Dynamic pressure Q is created from the velocity of the air and the air density. An increase in velocity has a dramatic effect on dynamic pressure Q, because it increases with the square of the velocity. Doubling the velocity means Q increases by 4 times. Increasing the velocity by a factor of 3 means that the dynamic pressure Q increases by a factor of 9. This is a very important concept in understanding the aerodynamics of WSC. Formula for dynamic pressure: Q equals V2x rho/2V equals velocity rho equals density factor lift. Lift opposes the downward force of weight and is produced by the dynamic effects of the surrounding airstream acting on the wing. Lift acts perpendicular to the flight path through the wing's center of lift. There is a mathematical relationship for lift which varies with dynamic pressure, Q, and the size of the wing. In the lift equation, these factors correspond to the terms Q, coefficient of lift, CL, and wing surface area. The relationship is expressed in Figure 213. Figure 213 shows that for lift to increase, one or more of the factors on the other side of the equation must increase. Generally, the lift needed is about the same for most flight situations. A slower speed requires a higher OO to produce the same amount of lift. A faster speed requires a lower OO to produce the same amount of lift. Because lift is a function of dynamic pressure Q, it is proportional to the square of the airspeed. Therefore, small changes in airspeed create larger changes in lift. Likewise, if other factors remain the same while the CL increases, lift also increases. The CL goes up as the OO is increased. As air density increases, lift increases. However, a pilot is usually more concerned with how lift is diminished by reductions in air density on a hot day, or if operating at higher altitudes. All wings produce lift in 2 ways. 1. Airfoil shape creates a higher velocity over the top of the wing and a lower velocity over the bottom of the wing with Bernoulli's-Venturi effect. 2. Downward deflection of airflow because of the curvature of the wing with the principle of Newton's third law of motion. For every action, there is an equal and opposite reaction. Both principles determine the lifting force. Review the pilot's Handbook of Aeronautical Knowledge to understand Newton's laws of motion and Bernoulli's-Venturi effect. Figure 214 top shows the amount of lift produced along the wing for an airplane wing with an elliptical planform. Notice how the amount of lift generated is smallest at the tips and increases slightly towards the root of the wing. This is known as the elliptical lift distribution. The WSC wing lift distribution is different because the wing twist at the root is at a higher OA than the tips. Most of the lift is produced at the center of the wing with less lift produced at the tips. The WSC lift distribution is compared to the lift distribution for an optimum design elliptical wing in Figure 214. Drag is the resistance to forward motion through the air and is parallel to the relative wind. Aerodynamic drag comes in 2 forms. 1. Induced drag, a result of the wing producing lift. 2. Parasite drag, resistance to the airflow from the carriage, its occupants, wires, the wing, interference drag from objects in the airstream, and skin friction drag of the wing. Induced drag is the result of lift, and its amount varies as discussed above for lift. Induced drag creates organized circular vortices off the wingtips that generally track down and out from each wingtip. Refer to the Pilot's Handbook of Aeronautical Knowledge for additional discussion on wingtip vortices formation. These wingtip vortex formations are typical for all aircraft that use wings, including WSC, PPC, helicopters, sailplanes, and all faa-crossed wing airplanes. The bigger and heavier the aircraft, the greater and more powerful the wingtip vortices are. This organized swirling turbulence is an important factor to understand and avoid for FLIght safety. Refer to the Aeronautical Information Manual, AIM, or the Pilot's Handbook of Aeronautical Knowledge, faa-h-8083-5, for additional discussion. Parasite drag is caused by the friction of air moving over all the components of the aircraft. Just as with lift, parasite drag increases as the surface area of the aircraft increases, and dramatically increases as airspeed increases, the square of the velocity. Therefore, doubling the airspeed quadruples parasite drag. Figure 215, the WSC aircraft can be designed for the purpose of being a slow FL-ying aircraft with a large wing where drag is not a major concern, or can be designed to be a fast FL-ying aircraft with a small wing where drag is more of a concern. The aircraft has plenty of items, area, for the wind to strike, including wing, wires, struts, pilot, carriage, engine, wheels, tubes, fuel tanks, etc. Parasitic drag can be reduced by streamlining the items. Round tubes can be streamlined, reducing the drag to 1/3, and cowlings can be used to streamline the pilot and the carriage completely, but not without the additional expense and additional weight of the streamlining. Streamlining does make a noticeable difference in the speed and gas mileage of the WSC, especially for the faster aircraft. Figure 216, with a large speed range of WSC aircraft, weight, complexity, amount and expense of streamlining, and resultant drag reduction are determined by the specific mission for the aircraft and the manufacturer's make and model. Figure 217, total drag is the combination of parasite and induced drag. Total drag equals parasitic drag plus induced drag. To help explain the force of drag, the mathematical equation D equals CDXQXS is used. The formula for drag is the same as the formula for lift, except the CD is used instead of the CL. In this equation, drag D is the product of the coefficient of drag, CD, dynamic pressure Q, determined by the velocity squared times the air density factor, and surface area, S, of the carriage and wing. The overall drag coefficient is the ratio of drag pressure to dynamic pressure. Induced and parasitic drag have opposite effects as OA decreases and speed increases. Note the total drag in Figure 218. It is high at the slowest air speeds at high angles of attack near the stall, decreases to the lowest at the most efficient airspeed, and then progressively increases as the speed increases. The WSC wing can FLY with a large range of airspeeds. Generally, the most efficient speed is at the lowest total drag, providing the best rate of climb, glide ratio, and cruise economy. However, slower speeds provide higher angles of climb, and faster speeds provide quicker transportation. Figure 218. Weight is a measure of the force of gravity acting upon the mass of the WSC aircraft. Weight consists of everything directly associated with the WSC aircraft in flight, the combined load of the total WSC aircraft, wing, wires, engine, carriage, fuel, oil, people, clothing, helmets, baggage, charts, books, checklists, pencils, handheld global positioning system, GPS, spare clothes, suitcase, etc. During gliding flight, weight is broken down into two components. The component that opposes the lift, acting perpendicular to FLIght/glide path, and the component that opposes the drag and acts in the direction of the FLIght/glide path. During gliding FLIght, this component of weight is the weight component providing the forward force, which some call thrust for gliding FLIght. During gliding, straight, and descending in unaccelerated FLIght, lift, L, and drag, E, components equals resultant force, RF, equals weight, W, total drag, DT, equals weight component, WD, in the direction of FLIght lift, L, equals weight component, WL, that opposes lift similar to airplanes, gliders, and PPC. During gliding FLIght, less lift is required because the resultant force composed of lift and drag provides the force to lift the weight. In other words, in gliding FLIght, drag helps support the weight. Figure 219, thrust at a constant airspeed. The amount of thrust determines whether an aircraft climbs, FLIES level, or descends. With the engine idle or shut off, a pilot is descending or gliding down. Maintaining a constant airspeed, when enough thrust is added to produce level FLIght, the relative wind stream becomes horizontal with the Earth and the OA remains about the same. As described for the airplane in the Pilot's Handbook of Aeronautical Knowledge, thrust equals total drag for level FLIght. Figure 220, When in straight and level, unaccelerated ight, lift, L, equals weight W, thrust equals total drag, dt at a constant airspeed. When excess thrust is added to produce climbing ight, the relative air stream becomes an inclined plane leading upward while OA remains about the same. The excess thrust determines the climb rate and climb angle of the ight path. Figure 221, when in straight and climbing, unaccelerated ight, lift, L, equals component of weight that opposes lift weight, W, equals resultant force, Fr, of lift, L, and excess thrust to climb, T, thrust equals total drag, dt, plus rearward component of weight. Thrust required for increases in speed above the lowest total drag airspeed, figure 218, faster speeds, lower angles of attack, for level and climbing ight requires greater thrust because of the increased drag created from the faster speeds. OA is the primary control of increasing and decreasing speeds, and increasing thrust generally does not produce higher speeds, but additional thrust is required to maintain level ight at higher speeds. Ground effect is when the wing is yin close to the ground and there is interference of the ground with the airfoil patterns created by the wing. At the same angle of attack, lift increases slightly and the drag decreases significantly. The most apparent indication from ground effect is the unexpected lift given to an aircraft as it flies close to the ground, normally during takeoffs and landings. More details for ground effect aerodynamics are found in the Pilot's Handbook of Aeronautical Knowledge. Flight characteristics for ground effect are covered in the takeoff and landing chapters. Center of gravity CG, the CG is the theoretical point of concentrated weight of the aircraft. It is the point within the WSC aircraft about which all the moments trying to rotate it during flight are balanced. The most obvious difference in the CG for a WSC aircraft is the vertical position compared to an airplane, as it is always lower than the wing. The Pilot's Handbook of Aeronautical Knowledge accurately states the CG is generally in the vertical center of the fuselage. The same is true for the WSC aircraft. However, the WSC wing is higher above the fuselage/carriage and, since most of the weight is centered in the carriage, the CG is well below the wing. In a two-seat WSC aircraft, the second seat is typically behind the pilot's seat and the CG is usually located close to the rear passenger seat. Therefore, the CG location does not change significantly with the passenger. Fuel tanks are typically located near the vertical CG, so any difference in fuel quantity does not significantly change the CG fore and aft with different fuel quantities. For level flight, the CG is directly below the wing/carriage attachment point known as the hang point, and the propeller thrust line is typically designed to be near the vertical position of the CG. Figure 222. Axes of rotation. The three axes of rotation intersect at the CG. Figure 223, lateral axis, pitch motion about the lateral axis, or pitch, is controlled by OA/speed and the throttle. Lowering the OA, increasing speed, rotates the nose down, while increasing the OA, decreasing speed, rotates the nose up. Increasing the thrust of the propeller rotates the WSC aircraft pitch up, nose up, to climb and pitch down, nose down, at reduced throttle. Longitudinal axis, roll turning is initiated by rolling about the longitudinal axis, into a bank similar to an airplane using aileron and rudder control. To turn, shift the weight to the side in the direction of the turn, increasing the weight on that side. This increases the twist on that side while decreasing the twist on the other side, similar to actuating the ailerons on an airplane. The increased twist on the side with the increased weight reduces the OA on the tip, reducing the lift on that side and dropping the wing into a bank. The other wing, away from which the weight has been shifted, decreases twist. The OA increases, increasing the lift on that wing and thereby raising it. Thus, shifting the weight to one side warps the wing, changes the twist, to drop one wing and raise the other, rolling the WSC aircraft about the longitudinal axis. Figure 224, more details on the controls that assist wing warping are covered in Chapter 3, which should be considered with use of the controls in the takeoff, landing, and flight maneuvers sections of this handbook. Vertical axis, yaw. The WSC wing is designed to fly directly into the relative wind because it does not provide for direct control of rotation about the vertical axis. Stability and moments. A body that rotates freely turns about its CG. In aerodynamic terms, for a WSC aircraft, the mathematical value of a moment is the product of the force times the distance from the CG, moment arm, at which the force is applied. Typical airplane wings generally pitch nose down or roll forward and follow the curvature of the upper airfoil camber, creating a negative pitching moment. One of the reasons airplanes have tails is to create a downward force at the rear of the aircraft to maintain stabilized flight, as explained in greater detail in the Pilot's Handbook of Aeronautical Knowledge. The WSC wing is completely different and does not need a tail because of two specific C design differences, a completely different airfoil design creating a more stable airfoil and lifting surfaces fore and aft of the CG, similar to the airplane canard design. WSC unique airfoil and wing design is shown in Figure 2.2. The WSC airfoil has the high point significantly farther forward than does the typical airplane airfoil. This makes the center of lift for the airfoil farther forward and creates a neutral or positive pitching moment for the airfoil. Most WSC airfoils have this unique design to minimize negative moments or pitch down during flight. Additionally, the design of the complete wing is a unique feature that provides stability without a tail. To understand the WSC aircraft pitch stability and moments, examine the wing as two separate components, root chord and tip chord. Trim, normal stabilized flight in Figure 225A. During normal unaccelerated flight at trim speed, the lift at the root, LR, times the arm to the root, R, equals the lift of the tip, LT, times the arm to the tip, AT. LRXR, plus, LTX at, equals 0 LR plus LT equals total lift of the wing, LW. Adding all the lift from the wing puts the center of lift of the wing, CLW, directly over the CG for stabilized flight. Figure 225A, if the pilot wishes to increase the trim speed, the CG is moved forward. This is done by moving the hang point forward on the wing. Similarly, to reduce the trim speed, the hang point/CG is moved rearward on the wing. High angles of attack in Figure 225B, if the wing OA is raised to the point of minimum controlled airspeed at which the wing begins to stall towards the center of the wing, root area, the lift in this area decreases dramatically. The CLW moves back a distance b creating a moment to lower the nose. Therefore, the center of lift moves behind the CG at higher angles of attack, creating a nose-down stabilizing moment. The average lift coefficient versus OA is shown for this minimum controlled airspeed in Figure 226. The root area is partially stalled and the tips are still FL-ying. The specific C stall characteristics of each wing are different, and this stall pattern shown here is used for example. Low angles of attack at very low OA, the tip chords are near 0 OA or below, not producing any lift, as shown in Figure 225C. At this point, the nose area is producing all of the lift for the wing. The CLW moves forward a distance c, creating a positive stabilizing moment to raise the nose. Pitch pressures as the pilot pushes out on the control bar. This creates a pilot input force that has a moment arm from the control bar up to the wing hang point. Figure 227, from this pilot-induced pitch moment, the control bar is pushed out, the nose raised, and the OA increases an equal amount for both the root and the tip chords. However, as shown in Figures 2-26 and 2-28, the average CL change is greater at the low OA at the tip chords, while the amount of change of the CL is much less at higher OA at the root chord. Therefore, an increase in OA for the wing results in the tips creating a greater proportion of the lift and moving the center of lift behind the CG, creating a negative pitching moment to lower the nose at high OA. Based on the same principle, when the wing OA is lowered below the trim position, the tip chord CL decreases more than the root chord and the center of lift for the wing moves forward creating a positive moment to raise the nose at lower OA. In situations where the pilot is FL-ying in severe/extreme turbulence, wind shear, or the pilot is exceeding the limitations of the aircraft, the WSC aircraft can get into a situation where the root chord is at a negative OA and not producing lift. This could result in an emergency vertical dive situation, as discussed later in the whip stall tuck tumble section. When at very low angles or negative angles of attack, the WSC wing is designed so that the wing has positive stability or a nose-up aerodynamic moment. This is accomplished by a number of different systems, washout struts, sprogs and reflex lines, further explained in Chapter 3 that simply keep the trailing edge of the wing up in an emergency low/negative OA dive situation. As shown in Figure 229, the root area of the wing has reflex which creates a positive pitching moment for the root chord to rotate the nose up towards a level FL-ying attitude. At the same time, the tips are at a negative OA producing lift in the opposite direction as usual, creating a moment to bring the nose/root chord up to a positive OA to start producing lift and raising the nose to a normal FL-like condition. The negative lift or downward force as produced at the tips and root as shown provide a positive moment to raise the nose back to a normal FL-ying attitude. Reflex also provides a stable pitch-up moment for an airfoil when it is FL-ying at normal FL-light angles of attack. The greater the reflex, the greater the nose-up moment of the airfoil. This is used in some WSC airfoil designs and also for trim control as discussed in Chapter 3. Carriage moments. The wing design is the main contributing factor for pitch stability and moments, but the carriage design can also influence the pitching moment of the WSC aircraft. For example, at very high speeds in a dive, a streamlined carriage would have less drag and, therefore, a greater nose-up moment because of less drag. The design of the carriage parts can have an effect on aerodynamic forces on the carriage, resulting in different moments for different carriage designs. The drag of the wing in combination with the drag of the carriage at various airspeeds provides a number of pitching moments, which are tested by the manufacturer, a reason the carriage is matched to the wing for compatibility. Each manufacturer designs the carriage to match the wing and takes into account these unique factors. Pitch moments summary. Overall, the amount of sweep, twist, specific airfoil design from root to the tip, and the carriage design determine the pitching moments of the WSC aircraft. Some have small pitching moments, some have greater pitching moments. Each WSC model is different with a balance of these aerodynamic parameters to accomplish the specific mission for each unique carriage and wing combination. Roll stability and moments as described in the Pilot's Handbook of Aeronautical Knowledge. More dihedral or less anhedral in a WSC wing creates more roll stability. More roll stability might be helpful for a training wing or a fast wing made for long cross-country straight flight, but most pilots want a balance between roll stability and the ability to make quicker turns and a sport car feel for banking/turning. Therefore, a balance between the stability and the instability is achieved through anhedral plus other important wing design features such as nose angle, twist, and airfoil shape from root to tip. An aerodynamic characteristic of swept wings is an effective dihedral based on the sweep of the wing and angle of attack. The combination of the physical anhedral in the wing and the effective dihedral due to wing sweep provides the balance of stability and rolling moments for a particular wing design. The design of the wing can have actual dihedral or anhedral in the wing. Even with anhedral designed in the inboard section of the wing, the outboard sections of the wing could have some dihedral because of the FLX and the outboard leading edges. As the wing is loaded up from additional weight or during a turn, the tips FLX up more, creating more dihedral and a roll stabilizing effect when loaded. Figure 230, generally, it is thought that the wing remains level and the weight shifts to the side to initiate a turn. Another way to look at how the WSC wing rolls is to examine the carriage and the wing moment from the carriage point of view. For example, the CG hangs far below a wing weighing 1/8 of the carriage weight. When the control bar is moved to the side, creating a moment about the carriage/wing hang point, the carriage stays vertical and the wing rotates around the carriage. Therefore, there are two rolling moments that both contribute to the WSC rolling into a bank. The pilot creating the force on the control bar rotating the wing about the wing/carriage hang point. Shifting weight to one side of the wing, thus warping the wing to aerodynamically change the lift on each side, as in airplane roll control. Figure 231, carriage moments. Carriage weight and resultant CG are the main factors that contribute toward increasing the roll moment for the carriage. Carriage aerodynamic forces are not typically a factor for rolling moments. Roll stability summary. Overall, roll stability and moments are a manufacturer/make/model balance between dihedral/anhedral, wing twist, nose angle, airfoil shape from root to tip, and leading edge stiffness. Some designs are stable, others neutral, and others can be designed to be slightly unstable for quick side-to-side rolling. Yaw stability and moments. There is no significant turning about the vertical axis because the WSC wing is designed to fly directly into the relative wind. Any sideways skidding or yaw is automatically corrected to fly straight with the swept wing design. An airplane uses the vertical tail to stabilize it to fly directly into the relative wind like a dart. The unique design of the WSC aircraft performs the same function through the swept wing design, but also the wing twist and airfoil shape from root to tip assists in the correction about the vertical axis. A simple way to understand the yaw stability is to see that any yawing motion is reduced simply through the increased area of the wing as it rotates about its vertical axis. Figure 232, there is a slight amount of adverse yaw similar to an airplane that can be noticed when a roll is faa-h-8083-5 initiated. The amount varies with the specific manufacturer's design and make/model. In addition, the wing can yaw side to side to some degree, with some different manufacturers make/model more than others. The higher performance wings with less twist and a greater nose angle are noted for less yaw stability to gain performance. These wings also require more pilot input and skill to minimize yaw instability through pitch input. In addition to the wing planform, twist, and airfoil shapes to minimize yaw, some wings utilize vertical stabilizers similar to these in airplanes and others use tip faa-ns. Figure 233, generally, the WSC wing is yaw stable with minor variations that are different for each wing and can be controlled by pilot input, if needed. Carriage moments. The wing is a significant factor in the design of yaw stability, but the carriage can be a large factor also. If the area in front of the CG is greater than the area in back of the CG, and the wing yaws to the side, then the front would have more drag and create a moment to yaw the WSC aircraft further from the straight ight. Therefore, phi and s are sometimes put on the carriage as needed, so the carriage also has a yawing aerodynamic force to track the WSC aircraft directly into the wind. Figure 234, since the carriage has such a large effect on yaw stability, the carriage is matched to the wing for overall compatibility. Each manufacturer designs the carriage to match the wing and takes into account these unique factors of each design. Yaw stability summary. These factors make the WSC aircraft track directly into the relative wind and eliminate the need for a rudder to make coordinated turns. Designs and methods vary with manufacturer and wing type, but all WSC wings are designed to track directly into the relative wind. Thrust moments. WSC aircraft designs can have different moments caused by thrust based on where the thrust line is compared to the CG. This is similar to an airplane, except the WSC aircraft has no horizontal stabilizer that is affected by propeller blast. If the propeller thrust is below the CG, figure 235, top, this creates a pitch-up moment about the CG when thrust is applied, and a resultant decrease in speed. When reducing the throttle, it reduces this moment, and a nose pitch down results with an increase in speed. If the propeller thrust is above the CG, figure 235, bottom, this creates a pitch down moment about the CG when thrust is applied, and a resultant increase in speed. When reducing the throttle, it reduces this moment, and a nose pitch up results with a decrease in speed. With a thrust line above or below the CG producing these minor pitch and speed changes, they are usually minor for most popular designs. Larger thrust moments about the CG may require pilot input to minimize the pitch and speed effects. Most manufacturers strive to keep the thrust as close as possible to the vertical CG while also balancing the drag of the carriage and the wing for its speed range. This is why the carriage must be matched to the wing, so these characteristics provide a safe and easy to fly WSC aircraft. Stalls, exceeding the critical OA. As the OA increases to large values on the wing chord, the air separates starting at the back of the airfoil. As the OA increases, the separated air moves forward towards the leading edge. The critical OA is the point at which the wing is totally stalled, producing no lift, regardless of airspeed, flight attitude, or weight. Figure 236. Because the OA of the WSC wing root chord/nose is so much higher than the OA of the tips, the nose stalls before the tips. It is similar to stalling with the airplane canard, in which the nose stalls phi-RST, the main wing, or tips for the WSC aircraft, continues to fly, and the nose drops due to lack of lift. In most normal situations, the root chord/nose stalls phi-RST because it is at a much higher OA. The tips continue to fly, making the WSC wing resistant to a complete wing stall. A pilot can even bring the aircraft into a high pitch angle stall attitude and keep the nose high. The nose stalls and rotates down because of the loss of lift, while the tips keep flying and maintain control of the aircraft. If flying within the operating limitations of the aircraft and the WSC reaches a high OA, the nose stalls, but the tips continue flying. However, it must be understood that there are many wing designs with many types of stall characteristics for each unique design. For example, high-performance wings could have less twist to gain performance, which could cause the wing to stall more abruptly than a training wing with more twist. Whip stall tuck tumble. A WSC aircraft can get to a high pitch attitude by flying outside its limitations or flying in extreme/severe turbulence. If the wing gets to such a high pitch attitude and the OA is high enough that the tips stall, a whip stall occurs. Figure 237, in a WSC wing, most of the area of the wing is behind the CG, about 3/4. With the tips and aft part of the wing having the greatest drag, and the weight being forward, an immediate and strong nose down moment is created and the WSC nose starts to drop. Since both the relative wind and the wing are rapidly changing direction, there is no opportunity to re-establish laminar airflow across the wing. This rotational momentum can pull the nose down into a number of increasingly worse situations, depending on the severity of the whip stall. Figure 237 shows a whip stall and the phases that can result, depending on the severity. Phase 1, minor whip stall, results in a nose-down pitch attitude at which the nose is at a positive OA and the positive stability raises the nose to normal flight, as described in Figure 225c. Phase 2, if the rotational movement is enough to produce a vertical dive, as illustrated in Figure 229, The aerodynamic dive recovery might raise the nose to an attitude to recover from the dive and resume normal FLI condition. Phase 3, the rotational momentum is enough to bring the nose significantly past vertical, the nose has tucked under vertical, but could still recover to a vertical dive and eventually resume a normal FLI condition. Phase 4, the rotational momentum is severe enough to continue rotation, bringing the WSC wing into a tumble from which there is no recovery to normal FLI, and structural damage is probable. Avoidance and emergency procedures are covered in Chapter 6, Basic Flight Maneuvers, and Chapter 13, Abnormal and Emergency Procedures. Weight, load, and speed similar to airplanes, sailplanes, and PPCs, increasing weight creates increases in speed and descent rate. However, the WSC aircraft has a unique characteristic. Adding weight to a WSC aircraft creates more twist in the wing because the outboard leading edges FLX more. With less lift at the tips, a nose-up effect is created and the trim speed lowers. Therefore, adding weight can increase speed similar to other aircraft, but reduce the trim speed because of the increased twist unique to the WSC aircraft. Each manufacturer's make/model has different effects depending on the specific design. As described in the Pilot's Handbook of Aeronautical Knowledge, the stall speed increases as the weight or loading increases, so some manufacturers may have specific carriage/wing hang point locations for different weights. Some require CG locations to be forward for greater weight so the trim speed is well above the stall speed for the wing. WSC aircraft have the same forces as airplanes during normal coordinated turns. Greater bank angles result in greater resultant loads. The FLI operating strength of an aircraft is presented on a graph whose horizontal scale is based on load factor. The diagram is called a VG diagram, velocity versus G loads or load factor. Each aircraft has its own VG diagram which is valid at a certain weight and altitude. See the Pilot's Handbook of Aeronautical Knowledge for more details on the VG diagram. Load factors are also similar to the VG diagram applicable to WSC. Basic propeller principles. The WSC aircraft propeller principles are similar to those found in the Pilot's Handbook of Aeronautical Knowledge, except there is no corkscrewing effect of the slipstream and there is less P factor because the carriage is generally FL yin with the thrust line parallel to the relative wind. The wing acts independently, raising and lowering the yaw and speed. This was introduced at the beginning of this chapter when angle of incidence was defined. The torque reaction does have a noticeable effect on the WSC aircraft. With a typical left-hand turn tendency, for right-hand turning propellers, turns are not typically built into the wing. As in airplanes, some cart designs point the engine down and to the right. Others do not make any adjustment, and the pilot accounts for the turning effect through pilot input. It should be noted that many of the two-stroke propellers turn to the right, as do conventional airplanes. However, many four-stroke engine propellers turn to the left, creating a right-hand turn. Consult the PO for the torque characteristics of your specific aircraft. Chapter Summary. Basic principles of aerodynamics apply to all aircraft. However, the unique design of the wing and the separate fuselage/carriage provide a simplistic and efficient aircraft. The following provide a summary of the unique aerodynamics for the WSC wing. The WSC wing is pitch stable without a tail because of the combination of airfoil design from root to tip, sweep, twist, and planform. WSC wing flexibility allows the wing to twist from side to side by shifting the weight, providing the control to roll the aircraft without control surfaces. The WSC wing only has two axes of control, pitch and roll, while no yaw control is needed because it is yaw stable. The WSC wing is stall resistant because under normal FLI conditions the tip cord is still FL yin while the rest of the wing is stalled, similar to the airplane canard system.